Hi there. Welcome back to the second part of chapter 7, our quantum mechanics chapter. And what we're going to begin with today are orbital diagrams, electron configuration, and noble gas electron configuration. One thing that's really important with this is that sometimes in a textbook, you'll have kind of like a cheat sheet, but that includes, so it's a only noble gas electron configuration, and sometimes it includes ways in which there are exceptions. The really big thing for this is that I'm going to want you to be using this method for figuring them out, not looking them up or memorizing them, because I want you to understand what you would see normally. That's what's really important at this stage, not being able to look them up and just write them down, because you need to understand where they're coming from. So in order to do that, let me go ahead and let's look at another example. So first of all, let's look at this one. Okay, so let's take a look just at this periodic, this piece from the slides. Okay, and this is slide 34. Okay, and now let's go ahead and take a look at what we have here. You'll notice here that I'm going to give this some different colors. Here you have your S block, and it includes helium over here. And last lecture, we talked a little bit about what that means. Okay, so remember that our S energy levels are go with L equal to 0, right? So when N is equal to 1, we have L equal to 0, and that's S. And the shape of those is kind of spherical, all right? And there's only one in each one, because when L is 0, you only have one M sub L value, and that's 0 as well. Okay, and each one of these can hold 2 electrons. Each orbital can hold 2 electrons, and we'll say spin up and spin down. That's why we have one S1 and one S2. So hydrogen, helium, okay, lithium, beryllium. Okay, so, and that's where that comes from. And that's 1s, 2s, and so forth. Okay, and this is going to show you, I want you to think about this in terms of order of fill. Okay, so now the next one that we have here is what we call our P block. Let's see if I can outline this. Right, so the other one is our S block, and this is our P block. Okay, and just as this is 2s here, this one is 2p here. Okay, and so the energy level for S and P are going to be the same. Now there's no 1p orbital because there's no L is equal to 1. All right, now let's take a look at our P block here. P comes from L equal to 1. And see how there's 1, 2, 3, 4, 5, 6 elements across in the P block? Well, that's because when L is equal to 1, our M sub L value is -1, 0, and +1. And each one of these can have 2 electrons, spin up and spin down. And that's why there are 6 of them as you go across. All right, now let's take a look at our D block, our transition elements. Here are transition metals. And here's our D block. Okay. And you have your periodic table. Hopefully still we'll be going to this in a minute. But you should have that with you all the time. And our transition elements are D blocks. Now notice our D block has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements in it. Well, that's because for D, we have L equal to 2. And there are 5 M sub L values that go with that. -2, -1, 0, +1, and +2. okay? And in each one of those, we have up and down. So we can have 10 electrons in those 5d orbitals. And then just as a little bit of a review here, remember that most of our p orbitals look a little bit like a three-dimensional figure 8. And most of our d orbitals look like a three-dimensional clover leaf. Okay. And now here we have our F block. All right, sorry about that. Okay. All right, so now here we are in our F block, and here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, and that is because when we have an F orbital, okay, and remember our F orbitals are sort of like this, and yes, the F's and the D's end up with some more. There. Okay. Now with these, we have L equal to 3 and M sub L equal to -3, -2, -1, 0, +1, +2, and +3. And in each one of these, we'll have, whoop, that didn't work. We'll have spin up, spin down, spin up, spin down, and there's 7 of them, so you know that you'll have 14. Okay, so then let's come back here for a minute and say, okay, well, in our s orbitals here, we have a total of 2 electrons. In our p orbitals, each one will have, we could have up to 6 electrons. Oh, I started to write protons there. We could have up to 6 electrons. In our d orbitals here, we could have up to 10 electrons. And in our f orbitals over here, we could have up to 14 electrons. Okay, now let's take a look then at where we're at. So let's take a look here and notice, so we have energy, n is equal to 1, n is equal to 2, n is equal to 3. And now let's look what happens when we get down to n is equal to 4, okay, because these are our n values. We have 4s, and then, okay, so we have 4s, and then 3d, and then 4p. And that's because the 4s energy level is actually lower in energy and more likely to be filled than the 3d orbital is. So it fills first. And that's because, you know, energy level 1 is going to be here, and energy level 2 is here, and energy level 3 is here. But once we get it up to energy level 3, you'll notice that your 4p and 4s kind of go like this. So you get 4s, and then you get your 3d here, and then 4p here. Okay, and they add a little bit out of order because it's all about, it's sort of like climbing stairs in a building, and it's, you come to the 4s before you come to the 3d. Okay, and that's going to end up being really important later. It's one of the reasons that, you know, your transition metals will form different charges, like you could have iron 2 and iron 3, or, you know, and different things like that. So there's some reasons in there behind that. We're also going to see that those d orbitals are going to allow us to do some really cool things with expanded octets. You're going to see the same thing when you get down here and you fill, so in energy level 6, first you fill your 6s, and then your 4f, and then your 5d, and then your 6p. Okay, and so that's what that is. So what I want you to do, if you haven't already done it, is go get your periodic table so that we can look at how we're filling those. Okay, I want you to have it sitting next to you, just like I have it sitting next to me. All right, so now, I just realized that, I don't know if you guys can see this, but the last column over here, it says 5p. Let me see actually if I can get that to, there we go. I think now maybe you can see it. Okay, so that last column there says 5p on it. Okay, now let's go ahead and look at this. So now actually, let's talk about some different things. So first of all, there is the word orbital diagram, and that's going to involve those boxes and the arrows. And then you have a couple different kinds of electron configurations. So let's take a look at where those come from. Okay, so first of all, let me go ahead and turn on the annotations again. Okay. Okay. Now let's start by saying, okay, well, here we have 1s and 2s, and now look at our 2p here. Okay. Now 2p, remember we have 3 p orbitals. So I'm going to subdivide that, or at least I'm going to try to subdivide that by drawing some divisions here. And then this one will also have, oh, okay, it's harder to draw here than you think. And so I'm making these, all these terrible. All right. Oh, and I just realized, I think, there we go. Okay. And so now, okay. Hey, there we go. Straight lines. Okay, and then our d orbitals we can put into 5 boxes. Yes, I wonder if there's a possibility of. All right, this, and then I don't know that that worked much. All right, and then so what I'm doing here is I am doing a terrible job of subdividing these. But what I did is I'm subdividing them into some different colors. Okay, so now let's come over here and let's take a look at some options that we have. Okay, so first of all, let's take a look, for example, at fluorine. All right, so say we're doing fluorine, and fluorine is number 9 on our periodic table. It's that first halogen. So take a moment and go ahead and find it. All right, now because it's number 9, we're going to have some different, we're going to be counting 9 electrons. Okay, so here we'll say, okay, well, we have 1 and 2. So the first 2 fill the 1s orbital. And then we have 3 and 4. Now you'll notice that we have 3 options here for p orbitals. Okay, so how are we going to fill those? Well, what we're going to do is we're going to fill them one after the other like this. So here we're up to 4. So now we have 5, 6, 7, 8, 9. And those are our 9 electrons. Okay, so now for fluorine, we can say, okay, that's our orbital diagram. Now let's say, okay, well then what is my electron configuration? And the electron configuration then for that is going to be 1s2, because I have 2 here, and then 2s2, because I have 2 there, and then 2p5, because I have 5 electrons there. And that's your full electron configuration. Now we can also write a noble gas electron configuration. And in a noble gas electron configuration, so I'm hoping that you can see this here. do this backwards. There we go. You can see fluorine up there in the corner. Okay. The noble gas that we come to before fluorine is helium. And helium is 1s2. So that means that the noble gas configuration for fluorine will look like this. We'll say, well, its core electrons look like helium. And then it has 2s2 and 2p5. Okay. Let's take a look at another one. Let's take a look at, trying to figure out what I've got where. Let's take a look at aluminum. And aluminum is number 13. Okay. So again, we're going to count 13. 1, 2, 3, 4, 5, 6, 7. Now you'll notice that I added all these up arrows first, and that's because we're not going to share a room if we don't have to. Okay, so that becomes 5, 6, 7, 8, 9, 10. Now I'm going farther. I have to go all the way to 13. So this becomes 11, 12, 13. Okay, and you can see here too that aluminum is the, let's see if I can find it. There we go. Aluminum is the first element in the P block for that level. Okay, so that makes sense. I just have one there. All right, and so then I come over and I say, okay, well, let's write our electron configurations. You don't have to do, so you only have to do the arrows if you're asked to find orbital diagram, okay? So we have, whoops, sorry. We have 1s2, 2s2, 2p6, 3s2, and 3p1. Okay. All right. Now, if we talk about our noble gas configuration, see this 2p6? That 2p6 goes with neon. So except for helium, we're always going to end noble gas configuration or begin noble gas configurations at the last full p orbital. So 2p6 is neon, which means that the core electrons for aluminum look like neon. And then after it, we have 3s2, 3p1. Okay, let's go a little farther. Let's do one more. And let's do one that's kind of higher up there, kind of looking for where we're at. And let's do, I don't want to duplicate anything that I don't have to do. Let's do selenium. All right, now selenium is number 34. So this is going to get big. Okay, so count and watch. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now we've got our d orbitals, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. We're getting close to our 34 now. 1, so 31, 32, 33, 34. Okay. And now for our electron configuration, we would have 1s2, 2s2, 2, whoop. Oh well. All right, I won't redraw that though. 2p6, all right, 3s2, 3p6, 4s2, 3d10, and 4p4. Okay, now for our noble gas electron configuration, you can see this 3p6 here belongs with argon. So the noble gas configuration for selenium says that the core electrons look like argon, and then we'll have 4s2, 3d10, and 4p4. Okay, so that's how we do electron configuration and noble gas electron configuration. Now come down here and take a look at what I have written down here. And here you'll see I have order of fill. So there's different things to show us order of fill. This is the one that I like to use if you're not using your periodic table. Honestly, that slide where I show where the periodic table fills, that's personally what I use. But this is the order of fill that you will be using. And the number here corresponds to how many electrons you have in that orbital for that element. Okay. All right. So let's go ahead and go back to another screen. Okay, so just to review, let's take a look at orbital diagrams, electron configurations, and noble gas electron configurations, sort of for one final moment. And let's go ahead and do that by looking at, you know what, we'll look at a really big one. Let's look at gadolinium. Oh my goodness, what is gadolinium? Check its spelling. Gadolinium is, the symbol for that is GD. And actually, let me go ahead and so here we have GD, and it's number 64, and it has down here 157. That's a 6 and a 4. Okay, so we have 64 electrons. Oh my. Okay, so what I'm going to do is I'm going to come down. Actually, here, we'll do this. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Wow, this is going to be crazy. 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. Let me pause there for a minute. We're going to remember that we have 40. I'll actually put it there so don't forget. Okay, so this is, and so I'm going to do the electron configuration then right here. Here we have 1s2, and then we have 2s2, and then we have 2p6, and then we have 3s2, and then we have 3p6, and then we have 4s2, and I'm just circling these in a way that denotes them. There's nothing specific whether they're circled or underlined. 4s2, and then after 4s2, we have 3d10 right here. 3D10, okay? And then we would have 4P6, okay? Oh, and then after 4P6, we would have 5S2, okay? Now after 5S2 comes 4D. And let's see if we can get 10 out of it. All right. So here we had said we were at 40. So 41, 42, 43, 44, 45, 46, 47, 48. So 48 will get us to 4D10. Okay. And then we're up to 5. Ooh, wrong color. All right, now we're up to 5P. Okay, and we were at 48. So we have 49, 50, 51, 52, 53, 54. Okay. So that gets us 5P6 at 54. Okay. 55, 56 will get us to 6S2. 56, we're almost there. Okay. So we're at 56. Now let's see here. After 6S2, we'll be up to 5D. Okay. 56, 57, 58, 59, 60, 61, 62, 63, 64. Okay. Now I'm going to check and see, did I do that right? Because I count 1, 2, 3, 4, 5, 6, 7, 8. Yes, gadolinium. So I have counted all of my 64, and here's that final D. Okay, and there's 8 of them there. So the final one here will be 5D8. Okay. And now we say, okay, well, what's my noble gas electron configuration here? So here's my orbital diagram. Here's my electron configuration. In order to find my noble gas electron configuration, I come to the last P6. And 5P6 will be xenon. Okay, so that means that for my noble gas electron configuration, I would say, okay, well, here I have xenon. Okay, and then everything after this, 6S2, 5D8. And if you were to look this up, you might actually get a different number. But again, that weaves in some exceptions that aren't really important until you're talking about more in-depth quantum. Right now, I want you to understand order of fill and where those orbitals are, because that's what's going to help us understand more about these orbitals and where they are for bonding and things like that. Okay, so this is what I will want on the recitation and on a test. Okay, so now let me come, let's see. The last thing that we want to look at today, and I'm actually going to go to the PowerPoint slides for this, is just to talk about some periodic trends. Okay, so what are those periodic trends? Okay, so first of all, here we have ionization energy. Okay, I think you can understand them, but first let's go ahead and look at a periodic table. Nope, that's not a good one. Sorry, I know that. All right. Before we look at that then, let me go ahead and let's go. I want to look at the periodic table first. Okay, here we are on the periodic table. Let's take a look at this for when it comes to periodic trends. So first of all, let's look at ionization energy. ionization energy is the energy required to remove an electron. So we'll say energy required to remove an electron. Okay, now as we go across the periodic table this way, it gets harder to remove an electron. So easier to remove an electron and harder to move an electron. And that sort of makes sense. You know that potassium becomes +1 very easily, okay? But bromine doesn't become +1, it becomes -1. Bromine isn't going to become +1 or 2 or 3. It's just not, because it can become a halogen by gaining only 1 electron. And we'll learn a little bit more about why going forward. But basically it has to do with an octet. This only has 1 electron in this energy level. So 1, 2, 3, 4. So this is N is equal to 4, energy level equal to 4. And potassium only has 1 electron in the N is equal to 4 energy level. And it's really easy to remove that 1 electron because it's only that 1 electron hanging out outside of the core electrons. It has argon and 1 electron, and that 1 lonely electron is really easy to remove. Now, let's take a look. In this energy level, we have potassium, and then we have calcium, gallium, germanium, arsenic, selenium, and then finally bromine. As we go across and yes, there's these d orbitals, but remember the full d orbitals are energy level 3. So we're not going to look at them right now. As we go across those, so now by the time we get to bromine, we have all of these extra protons in the nucleus, but we're still in the same energy level. So we're not farther away from the nucleus. Everything in that energy level is at about the same distance from the nucleus, but there's more protons in there pulling harder on those electrons. So basically, bromine's electrons see more of the positive charge from the nucleus. And because there's more of that positive charge in the nucleus pulling on those electrons, it makes them harder to remove them, more difficult. It requires more. So as we move across the periodic table, our ionization energy increases. Okay, now let's take a look at what happens when we move down the periodic table. So let's say that we're moving down the periodic table like this. As we go with each level down the periodic table, we see that the energy levels, each energy level before it shields the outer electrons. So for example, let's look at this potassium. Well, actually, let's look at sodium here, and then let's look at cesium. Okay, so sodium is in N equal to 3. So it has 1, 2 layers of core electrons there, shielding it from the nucleus. And so it only has to, so sodium's electron only has to look through 2 layers to see the nucleus. If we come down here to cesium, 4, 5, 6, N is equal to 6, cesium has 1, 2, 3, 4, 5. So that last electron in cesium has to look through 5 layers of electrons in order to see the protons in the middle. So even though there's way more protons, all right, so even though cesium, there's way more protons in cesium, cesium has to look through those blankets of electron layers of negativity in order to see it. Because cesium's valence electrons, its outer electrons, are so far away from the nucleus, then it actually gets easier to remove an electron. So it's easier, oh, where's my cursor? There we are. It's easier to remove these electrons, and it's harder to remove the ones that are up high. Okay, so the ionization energy gets larger as we move across the periodic table and smaller as we move down the periodic table. And what that does is it gives us an overall trend that looks like this. Okay, so the smaller ionization energies are going to be down here, and the larger ionization energies are going to be here, and everything moves in that direction. So that's what you can use for coming up with those trends. Okay, we do see, let me clear these now, we do see some ionization energy exceptions. IE exceptions. Oh, and I'm still on a very large, there we go. Okay, so where are those ionization energy exceptions? Well, they happen basically whenever we move into a new segment that makes it a little bit easier. So remember, lithium and beryllium, this is right here, okay? Lithium and beryllium, this is 2s2, 2s1, 2s2. This is a full S shell. Now, boron is the beginning of the P block. Okay, and so you could say that it's got one here, and then carbon will be up and nitrogen will be up for those. Now, again, we see another exception at oxygen because oxygen is the first one that has to double up. So what that means is that means that it's harder to remove. So it's easiest to remove lithium, and then it's harder to move beryllium, but then it's a little bit easier to remove boron, and then harder to move carbon, harder to move nitrogen, and then a little easier to remove oxygen. And that's because when this boron electron is all by itself, it doesn't really have to worry about anything else there, and it's easier to remove it because it doesn't have a buddy. It's also the 1s, the 2s2, sorry, the 2s energy level is full and complete. And then boron's got this little thing up here in the 2p's, and it's all by itself, and it's really easy. It's easier to remove that. Now with oxygen, you all of a sudden the oxygen, so boron, carbon, and nitrogen, each one of those get one of their own little p orbitals. Oxygen has to share, and they don't like that. And what you do is you see this electron pair, you see this repulsion, electron repulsions here when they're asked to share an orbital. And that's why oxygen, it's a little easier to remove it. Okay. All right, let me show you the slide for that. Okay. Okay. Oop. Oh, sorry about that. Sometimes, there we go. That one. Okay, so take a, and you'll see this. This is the exceptions in the ionization energy. Okay, so here you have lithium, beryllium, and then down to boron, carbon, nitrogen, down for oxygen. And then you see it here too, sodium, magnesium, and down for aluminum, silicon, phosphorus, down for sulfur. So you'll see that all the way across the periodic table, and it's the first electron in the P block is a little easier to remove than the second electron in the S block, and the fourth electron in the P block, the one that has to start doubling up and sees those electron repulsions, is a little bit easier to remove as well. Okay, and now we have another key. I want you to read about electron affinity. We don't go into as much detail about it because it's I'm trying to, there we go. We don't read as much about electron affinity because it is it's a little bit harder to predict. I'm looking for it. There we go. Okay, now, oh no, I'm sorry. I do want to be here. Now the next thing that we see is, here we go. Sorry. I apologize. I'm having technical difficulties trying to figure out what's wrong here. Okay. I apologize for that. Okay, so I believe, come on, there we go. Okay, now let me try this again. Share screen. All right. And again, I'm just in these slides. Hopefully you guys have seen them at this point. And let's talk a little bit about the next one. Let's talk about atomic radius. Okay. Now this is basically, this is a periodic table, right? It's this with just some of our key ones. And an interesting thing here, this is going to be a little bit backwards from what you expect in a way. Now, remember when we were talking about ionization energy, and we said that as we go down the periodic table, we have those core electron shells that it's harder to see through. And you'll see that again. Every single energy level is bigger and farther away. So when you're talking about atomic radius and atomic radii, this is the same size as saying the size. Sorry. Try that again. All right. Size of atom. Okay. The atomic radii, so you have your sphere here. And the radius is this center line, okay, from the center of our sphere. Okay, just assuming that we're mostly spherical. Okay, so based on that, that makes sense. As we go down the periodic table, each energy level is farther from the nucleus. So here we are smallest, and here we are larger, or yeah. So we'll change this to smaller and larger just because it's a little easier. Smaller to larger, okay? Now, that makes sense. The next trend doesn't make as much sense. As we go across the periodic table like this, you would expect that we're adding protons and we're adding electrons, so we should be getting bigger, right? We're adding a lot more mass, so we should be getting bigger. And what we actually see is exactly the opposite. As we add more mass, as we add more protons and neutrons to that center nucleus of extremely dense charge, we are adding more pull to the outside electrons. So we're actually pulling them in tighter. So even though we're adding mass, we're actually getting smaller, okay? So this side of the periodic table is smaller and this side is larger, okay? And so that means that our overall trend here comes down like this, from smallest here to largest here. Now, one thing that I want you to be very careful of is, as you can see, there aren't many exceptions to atomic radii. The atomic radii trends are almost foolproof each way, just as we go along the periodic table. However, there are trends in ionization energy that are exceptions, and they are notable exceptions that are very important. So you won't see the same pattern always with the trends. So what you'll see is so if you have one trend for ionization energy, you won't always see the same trend mirroring it for atomic radius. So sometimes you'll see a mirror image trend from ionization energy to atomic radius, unless you're dealing with exceptions, and then you will not see that mirror trend, okay? As usual, let me know if you have any questions, and I will hopefully see you all in recitation sessions. Bye.